morning, good afternoon, or good evening, wherever in the world you are joining us for this PSS webinar series, actually. I mean, I don't know if you've been with us the days before. Today, we will talk about GPC SEC applications. My name is Derek Lohman. I'm with PSS in the United States of America, based out of Amherst, Massachusetts. And your presenter today is Dr. Daniela Held from our main office in Germany. She joined PSS in the year 2000, and she is the head of basically marketing. And she will be talking to you about GPC SEC applications. Before we do that, a couple of reminders regarding the general flow of our webinars. The webinars are listen only, meaning you are not allowed to talk. However, we welcome any question that you may have in the questions tab, and we will answer all those questions at the end of the webinar. In addition to that, the webinar will be recorded and will be made available under the same link that you used to register for this webinar as soon as this webinar is basically transcoded and uploaded. In addition, you are always very welcome to request a PDF of the slide deck that Daniela will be showing. Just send an email to either Daniela or myself, and we're more than happy to send you a PDF of those slides. And I think I've covered everything that there is to know. So with that, I think I would hand over to Danny to talk to you about GPC SEC applications.
Thank you, Derek, for the introduction. Derek already mentioned that we do have a series of webinars with today's title, today's title, GPC SEC applications. We cover several subjects. This subject here, GPC SEC application, was brought to us by one of our attendees from one of the previous webinar series. And actually, I volunteered for this topic because I really think it's very important to know or to have a good idea about the GPC SEC applications. When I prepared the slides or the topics for this talk, I was kind of unhappy with my decision to volunteer for that because I really thought that we do cover a wide area here. However, I think we'll have fun in the next 50 minutes because you will see how interesting GPC SEC can be. So what question do we want to answer today? We want to answer which questions GPC SEC can answer and what results GPC SEC can provide. So what is the contents of today's presentation? I already mentioned that we cover a lot of different topics. We'll start first with a short introduction on GPC SEC in general, very brief and only with the very basics. We will then discuss how to measure molar mass distribution. I will comment on composition distribution and branching analysis and what GPC SEC can do with respect to these topics. Then we'll have a look at regulations for polymers because GPC SEC is very important to classify products, and one of the major methods or the methods mentioned when you need to register a product or a chemical. Then we will have a look at the characterization of porous materials. Here we will discuss two options. And last but not least, I want to show you a short introduction on what GPC SEC can do with particles. To be completely honest, it's not true GPC SEC, what we are discussing there, but I think you'll get the idea when we look at the slides there, what is happening there, why I have added this to this GPC SEC application presentation. And last but not least, I have a final summary slide before we will answer your questions. So let's start with a very brief introduction and a very full slide in the beginning, because this is actually what we are facing. When we talk about GPC SEC applications, I think everybody knows that we will definitely talk about macromolecules, because GPC SEC is the method of choice to characterize macromolecules. Why are macromolecules difficult? They are difficult because we have to deal with distributions. You see here in the center of the slide the molar mass distribution, which is present for all synthetic polymers and for the vast majority of all natural macromolecules. So we always have to deal with molar mass distribution. Additional distributions, as you see here on that slide, could be there, like we can have different end groups, we can have branching, we can have, of course, the large group of copolymers with the block copolymers, alternating polymers, or gradient polymers. We also have the different structures as mentioned. So polymers by themselves are very complex molecules because we have to deal with distributions. So, as already mentioned, the standard LC method, the standard liquid chromatography method for the separations of macromolecules is GPC, SEC, or GFC. And here we already start with the first problem, because it really depends on whom you talk to, how this technique is addressed. GPC, gel permeation chromatography, is mainly used for the separation of plastics and synthetic polymers and organic solvents. When you look at people who investigate proteins or polysaccharides in aqueous solvents, they will most of the time they will speak, or they will talk about size exclusion chromatography, SEC. And when you talk to biologists who really don't care much for in-depth characterization, but more for the fractionating power of GPC, SEC, GFC, they will call their technique gel filtration chromatography, GFC. So all these three abbreviations stand for the same liquid chromatography technique. SEC is by far the most descriptive term for this kind of separation, as it already has in its name that we are doing size exclusion, that we separate by size. Here on this slide, you see as a slide reminder of how GPC SEC works. We have, of course, a column which is filled with porous material of a different particle size, and most important are the pores indicated here. They are responsible for the separation. At the top, we'll inject a complex mixture indicated here by different sizes being related to different molecular weight, and also it can be different chemistry. What happens when we inject this complex mixture on our column? We'll have that size separation, meaning that large molecules cannot penetrate the pores. That means they are excluded, and they will elute first, as you can see here with the red molecules. The blue molecules, medium size, they fit in some of the pores and will diffuse into the pores they fit in, but of course they do not fit into all pores, so they elute as a second peak. And the small green molecules, they fit in all of the pores. This means they need the longest time to travel through the column and will elute last. So SEC is a pore size limited, diffusion-based liquid chromatography technique. Really important is always to remember that the separation is based on hydrodynamic volume and not on molar mass. Of course, molar mass contributes to hydrodynamic volume, but it may not be the only factor or the only parameter contributing to your hydrodynamic volume. So it's always important to remember that we separate based on this parameter, on hydrodynamic volume. And of course, interactions between the stationary phase and the analyte need to be avoided. I already mentioned that one of the main applications is to get molar mass distribution results, and this requires a calibration. So let us look on the next slide, where we discuss the fields of application in more detail and what will be covered today in this presentation. I already mentioned that GPC can be used as a fractionating technique, sometimes even without using a detector, just collecting the different fractions. This is shown on the top left. We will not cover that in detail today. What we will also not truly cover today is when we look at complexes with macromolecules, or when we look at proteins, at protein purity or protein aggregation. You see here an example of this typical application here, where we separate a dimer from a monomer and where we quantify the amount of dimer. This can be added with molar mass information as it's shown in the example here, but this is the only application here for the proteins that you will see here in the following presentation, because in this presentation, we will mainly concentrate on determination of molar mass, meaning starting from simple sample comparison to results for quality control or research and development. But I also want to show the power of this technique when you want to determine pore sizes. So we'll have a more detailed look at inverse GPC or at sieve curves and sieve curve analysis. To summarize the field of applications, GPC is used to separate and characterize complex mixtures. It is a versatile technique for R&D, product development, and quality control. And the good thing is that there are hardware and software solutions for very specific tasks. Here at the bottom of this slide, you will see on the left-hand side a very easy setup, a very easy GPC SEC setup, where we just have simply overlaid for visual comparison several mineral oils. Such sample comparisons, as I said, can be very easily done. They are used, like, for example, for degradation studies, or when you want to look at the kinetics of a reaction. This is, on one hand, a very, very simple technique. On the other side of the slide, on the right-hand side of this slide, you will see size exclusion chromatography as part of a two-dimensional separation. In this example, you will see a polystyrene polymethyl methacrylate graft copolymer, which is nicely separated by chemistry in the first dimension and by size or molecular weight in the second dimension. So you see already here that even if when you talk about simple size exclusion chromatography for molar mass determination, there can be very different setups which might be required. So with this short introduction, we will get a little bit more into detail and look at some applications. We'll start with molar mass distribution, composition distribution, and branching analysis. Here on this slide, you see a blue curve, and this is actually the thing that you will get out of a GPC SEC instrument with one detector. You will get a detector trace, a detector signal spread over a certain elution volume. So this blue information is what you get out of your detector. Unfortunately, this information here has contributions from both, from your sample itself and from the setup you're using. For example, the number of columns determines the elution volume, and also the resolution power of your columns determines how broad the peak might look like here. Without any additional information, there's not much we can gain here. I can, for example, compare with another trace from like last week, and I can say, oh, it's the same or it's shifted, but there's not much information I get out of here. However, this changes when I have my calibration curve, and this is the red curve you see here. This is the logarithm of the molar mass plotted versus the elution volume. And as soon as I have this information available, I can get my molar mass distribution. Please note that the x-axis as also the y-axis have changed here. While we have on the left-hand side elution volume and detector intensity or signal intensity, on the right-hand side we do have the logarithm of the molar mass and W of logarithm of molar mass, which means the fractions at a certain molecular weight here. So we have a true molar mass distribution here. We see the curve here. And of course, from this information, we can generate the molar mass averages, like the number or the weight molecular average. And we can also get, of course, the polydispersity of the samples. So once we have a calibration, or once we know which molecular weight elutes at which elution volume, we can get detailed information like the molar mass distribution, very detailed information. So how can I create such a calibration curve? There are in general two ways to create such a calibration curve. We can use standards or reference materials. We can use different molar mass standards with a narrow molar mass distribution or broad distribution standards. The other way is that we use specialty detectors like online light scattering detectors, viscosity detectors, or the mass spectrometers. All these detectors will allow us to measure the molar mass at a specific elution volume. Important is that you do not confuse an evaporative light scattering detector with the light scattering detector shown here, which is a light scattering detector in solution, because evaporative light scattering detectors are basically concentration detectors. You cannot measure the molar mass using, or the absolute molar mass using an evaporative light scattering detector. For this, you would need a light scattering detector in solution. So let's have a look at some selected examples and recommended calibration techniques. In QC, you very, very often use calibration with reference materials. The most common approaches are here that you use narrow standards, but you can also use broad standards, and this is becoming more and more popular because, of course, ideally, you want to match the chemistry of your sample with your calibration standards. And since you cannot generate narrow molar mass distribution standards for all chemistry, broad calibration has become really important over the last years. For example, when you look here at heparines or also at dextranes, there are several broad calibration routines that are used for these important molecules, and they are described in, for example, the US Pharmacopoeia or the European Pharmacopoeia, and they really relate to this broad calibration standards so that you can have a successful quality control of your samples. When you look at R&D departments, you also see all kinds of stuff. You have here calibration with standards, but you also have universal calibration, for example, where you use a viscosity detector or the mathematical approach. And also, of course, a lot of R&D labs use online light scattering detector to measure the molar mass distribution. So here, getting the molar the information you want to is very, very application dependent. I just want to show one more application or discuss one more application here, which is the application of hydroxyethyl starch for USP. Here, for example, it's one of the rare examples where you have a quality control with a detector where you are required to use multi-angle light scattering detector if you want to use the technique that is recommended by the USP. Just a short reminder how you create a calibration curve with narrow standards. It's quite easy because you just use like 10 or 12 standards, which cover the complete molar mass separation range of your columns. What you then do is you measure this chromatogram I've shown you on one of the previous slides, and then you can just read the elution volume at the peak maximum, relate that to the molar mass at the peak maximum, and then you have a calibration table with different molecular weights, and you have calibrated the column, the elution volume range of your column with that. How does it work with broad standards? I just want to show you here the cumulative match calibration that I already mentioned for the heparines. Because here you have just one standard, one broad standard, and you have a very detailed list of molecular weights for this standard. So as an example, you see here that, for example, at 10% eluted mass, you have a molecular weight of 26,900 Dalton. For 30, you have like 55,100, going up to 90% eluted mass, you have a molecular weight of 195,000. So what you do is you measure this broad standard on your column set, on the column set you want to calibrate, and then you can just read from the integral curve here, the cumulative match curve here, at 60% the elution volume, and can assign that to the molar mass of your certificate, so that you will end up with a table like here, but much more detailed. I'll show it to you in an example with the heparin, with the USP standard. You see here in green the chromatogram, here the automatically determined curve of eluted mass, and then you can just assign all the different molecular weights reflecting the different parts of elution here, and have with one injection, with one standard, a calibration, a chemically matching calibration for your unknown heparins that you want to characterize. So there's much more in GPC than just narrow standard calibration, and as I mentioned, over the last years, broad standards have become more and more important because they are easy to use, they are fast to use, and of course cheaper to use and easier to use than more advanced equipment. Nevertheless, there are some applications where you cannot use calibration standards because they're just not available. For example, when you look at very high molecular weight samples like the starches I've shown in this application here, then you will immediately see that we are covering very, very high molecular weights, like 10 million here in that range, and even higher, going up to 100 million molecular weight. And I think it's quite clear that there are no matching standards for this application. So what you can do here is that you use a light scattering detector. And you see here the molar mass distributions measured with my light scattering detector and compared. We have here, for example, different starches or different sources for starches, and we have investigated the native and the milled state, so that you directly see here in the overlay of these molar mass distributions what happens during process. For example, for maize starch, you see here the native sample, sorry, in dark red, and here in orange you see the molar mass distribution after processing, after the sample has been milled, and you directly see here the differences between the different starch types, and also that processing affects different starch types differently. Of course, you need to remember that for such high molecular weights, you need to be really careful with your chromatography. You need to adjust concentrations, you need to adjust flow rates, you need to have matching columns for that with larger particle sizes. But of course, that is all part of the application here. So if you have chosen the matching conditions for your application or for these high molecular weights, then you can measure them very easy and very reproducible with GPC SEC. Let's have a look on the other applications you can do. You can measure very high molecular weight samples, as you've seen in the previous slide. You can also measure very low molecular weight samples. For low molecular weight samples, you can achieve a very high resolution. This is something which you'll never get for high molecular weights. For high molecular weights, you will always get broad peaks, but for low molecular weights, depending on the resolution power of your column, you can even get single peaks for your oligomers, or as you see here in this example, you can even see residual monomer as a single peak, or residual solvent or other impurities in your sample. So what you can do besides measuring the complete molar mass distribution for such a sample and for determining the molar mass averages is that you can quantify. That means you can just work like you would do it in HPLC. For example, if you have If you know your monomer, you just inject your monomer and you can identify where the monomer eludes. From the area, you can get the percentage area value without any additional information. If you do a detector calibration, then you can also get the concentration. And important to know for the detector calibration is that it's totally different of the calibration we've been talking previously about. For the detector calibration, you take your monomer and you inject several concentrations of your monomer, and then you get a response factor for the detector for your monomer. And using this response factor, you can calculate the concentration from the area. So like you would do it in HPLC. So for low molecular weight samples, it's very often possible to get both the molar mass distribution plus an additional quantification in the low molar mass area. With this last example, with it showing the two extremes like low and high molecular weights, we'll change the subject a little bit because I think I could have shown some nice applications where you measure the molar mass distribution. However, sometimes or a lot of times people also have copolymers and are interested in having a look at the changing compositions, for example, in block copolymers. For this, GPC SEC can be used for some selected application using dual detection. And with dual detection, I mean, in this case, just a simple combination of two different concentration detectors. So no molar mass sensitive detectors here, no viscosity detector, no light scattering detector, just very basic refractive index RI detection or UV detection or IR detection if possible. As an example, I've picked here a very nice example from high temperature GPC SEC. I think most of you are aware that polyolefins cannot measure in ambient GPC SEC because polyolefins do not dissolve at low temperatures. You have to use very specific solvents at very high temperature to keep them in solution and to enable GPC SEC separation. On the upside, there's also an advantage because the solvents you are using allow IR detection, something which is not possible in ambient solvents like THF or chloroform or toluene. So when you're using high temperature GPC and you have here, like for example, an ethylene vinyl acetate copolymer, you can monitor the change in composition by comparing the two detector signals. Here, I'm sorry. Here in this example, you see a red trace, which is the RI detection where we monitor the CH2 group. The green trace here reflects the CO group because we specifically detect the CO group here. And what you see is that the red trace and the green trace look very different. And this different indicates already that you have a difference in composition. And so what we did is we used both of these traces and we calculated the relative vinyl acetate content from the green and the red trace. So you see here the black trace, and at the beginning at high molecular weights, you have a relative low vinyl acetate content. This changes completely when you go to higher elution volume and thus lower sizes. Here you have a very high vinyl acetate content. And this kind of dual detection can be done very easy. You see here that we just need two different concentration detector signals. This would, for example, also work for the polystyrene PMMA copolymer I've shown you in the beginning. So every time you have like two comonomers reacting different to concentration detectors, you will be able to have at least an idea if you have an identical composition through overall molar masses or if the composition changes with your molar mass here. So this can be done in both ways, very simple like we've done here, but of course you can also quantify that and use 2 different calibration curves and can then measure the molar mass distribution of your block copolymers. So this was my example for measuring the chemical composition. What about branching? Branching is very important for macromolecules, and we speak of branching when there is at least one branching point combining 3 or more chains. Why is branching so important for us? Because of course branching affects the macroscopic properties of my macromolecules. It will affect the class temperature and solubility, and most important, I think, for many applications, the viscosity of my sample. Here you see an example Mark-Howing plot where we plot the logarithm of the molar mass versus the logarithm of the intrinsic viscosity. So basically we monitor how the intrinsic viscosity or how the viscosity will change when molar mass increases. You see here the behavior in black for a linear molecule, and then in blue and later in green for star polymers. A 3-arm star is the, let's say the simplest approach to a branched molecule. And you will see already that at the same molecular weight, a branched molecule has a significantly lower viscosity than a linear one. So viscosity is a good way to learn more about branching because it is so strongly affected by branching in my molecule. So let us look at some real data. Here we used GPC SEC viscometry to determine long chain branching. This is a very sensitive tool. In principle, you could also use a multi-angle light scattering detector, but I personally prefer viscosity over the Maltz detector in this case, because for viscosity, the extrema go from a slope of 0 for a solid sphere to a slope of 2 for a rigid rod, while the area, the range is much smaller for the radius of gyration. So for a multi-angle light scattering detector, this would vary only in the range of 0.33 to 1. So viscosity detector is the detector of choice to investigate long chain branching. And this is what you see here in this Mark-Howing plot. We have here a linear sample in purple, and here in blue a low density polyethylene with long chain branching, and you can directly see that we do have a branched sample here because at the same molecular weight we have it shifted to a significantly lower viscosity. What I cannot measure with GPC SEC viscosity or viscometry is short chain branching. Here you see also overlaid linear low density polyethylene, which exhibits short chain branching, and you will see that our viscosity detector is blind for the branching here. Short chain branching is not affecting the viscosity so much that we can measure it using the GPC SEC viscosity detector. What can we do in that case? Fortunately, there is a solution for the polyolefins here, because in high temperature GPC, I already mentioned that you can use IR detection. And here with the IR detection, it's also possible to determine the short chain branching. The approach would then be, again, that you use some kind of dual detection where you look at different vibrations in your molecules so that you are able to determine the short chain branching. For both, for composition analysis and for branching analysis, I've shown you now some examples that you can apply in GPC SEC. However, I want to motivate you to not only think about GPC SEC here, there are other techniques, separation techniques for macromolecules, like here, for example, IPC interaction polymer chromatography or related alternative chromatographic techniques, where you can learn more about your branching or about your composition than you could learn from GPC SEC. If you are lucky, GPC SEC provides very important answers for you. It really depends on the application, but it might be that your application requires a different approach here. So with that, I want to change the subject a little bit because I also promised you that we would look at regulations for polymer, because size exclusion chromatography is very important if you want to register or if you want to learn more about your polymers, or if you want to prove that you do have a polymer. I think a lot of you will be very familiar with these abbreviations above. We have here PLC, which means polymer of low concern, or REACH or K-REACH. REACH is a regulation in the European Union. K-REACH is a regulation in South Korea. And all these regulations in all the different countries around the world, they are there to protect us, to provide safety for us and for the environment. And a lot of the times polymers are exempt from registration. Why is that the case? This is the case because in general they are biochemically inert and not posing any threat to humans when we consume them. The molecular weight is so large that there is no hazard for us, for humans, or for biological mechanisms if we are confronted with a macromolecule. This is of course different for unreacted monomers, oligomers, or other additives in our products, in our polymers. They are the potentially toxic subjects. And this is why we need to really look at those low molecular weight compounds and about the amount of them in our product. So as mentioned, polymers are often exempt from registration, but I need to prove that I do have a polymer. And if I do have that, or the molar mass defines if I do have a polymer or not, and defines thus the registration category. So GPC SEC is a method for molar mass determination. And so this is why it is important when you look at registrations and, for example, at polymers of low concerns. Here, the definitions and required characteristics for PLC in different countries is very, very different. However, the same, or when I need to pick out the same information, then I can say that in nearly all of them, GPC SEC is used to provide the required molar mass information. I need the number average molecular weight or mate average molecular weight, and I certainly need the mass fractions below 500 Dalton or above 1000 Dalton. So how does it look like? Very similar to that what I've already shown you. We do have the molar mass distribution. From this molar mass distribution, I can get my molar mass averages. And now I have an additional information here because I look at the fraction below 500 Dalton and the fractions of above 1000 Daltons. I have the numbers here, and these numbers define if we can speak of a polymer of low concern or not. So very often, for customers in our analytical department, for example, they do not only want to know the molar mass averages and the polydispersity or the dispersity, they also want to know the fraction below 500 Dalton and above 1000 Dalton, so that they can prove that we are really talking about the polymer, and so that different rules apply. What about REACH? REACH is a little bit more difficult because for REACH, the criteria are a little bit different. For example, here you need to prove that your molecule shows a molar mass distribution. You need to show that the mass percentage of molecules with 3 or more monomer units are above 50%. and that the mass percent of each molecule with the same molar mass is less than 50%. So when you look at this, you will immediately understand why GPC SEC can help you here. And I'll show you in an example because I think then it's easier to understand. In the background, you see just a simple GPC SEC chromatogram. I have here a very nice resolution. We have an oligomer here, an oligomeric resolution, and I can identify several peaks. And now I create a list showing me the content, which is the area underneath the peaks, which is the molar mass we got in this case from polystyrene equivalents. And then we'll just look if the criteria from REACH apply. Let's start with the easiest one. Yes, we certainly see a molar mass distribution. Second one here, no individual chains above 50%. Yes, we can confirm that there are no individual chains with more than 50% molecular, 50% content, sorry. And last but not least, we look at the rule of 3 monomer units plus 1. For this, we've identified the 3 monomer units here, and we can also confirm that less than 50% are below 3M plus 1. So in this case, we can decide, reviewing that table, yes, we do have a polymer, and this should be exempt from REACH. Many countries around the world have their own REACH regulations now. For us, we are dealing at the moment a lot with K-REACH. This is very similar to REACH, but if you have to register your products in Korea, you should be aware that there's significantly, or that we at least observed a significantly higher effort for the analysis itself and for the documentation. I personally think they have done that in a very nice way. They really force us to do good GPC SEC and really are looking into the numbers and into the details of each analysis. And it's not a problem to do it. It's just that more documentation is required and that you really need to review what is required for K-REACH. Okay, let's come back to our contents in general, and let's have a look how we can characterize porous materials, because until this stage we only have looked at chains, we had looked at branch chains, but now what can we do with porous materials? Is there also something I can do using GPC SEC? Yes, there are 2 techniques that are applied, and what we will discuss today here is, first of all, sieve curve analysis and inverse GPC SEC. What kinds of materials, of porous materials, can be investigated? You will see here as important materials at sponges or foams, membranes, very, very important, tissue cells, also extremely important, and what brought us into the fields, of course, stationary phases in chromatography columns. They are also porous materials, and this is why we were interested in those subjects, very, very much interested in those subjects first. Both techniques that we will discuss, sieve curve analysis and inverse size exclusion chromatography, will allow us to measure pore sizes and, very important, their distribution. Let us first have a look at membranes. Membranes are usually characterized using sieve curve analysis. Here at the bottom, you will see 3 different cellulose membrane sieve curves. As an x-axis, you have here the pore diameter, and on the y-axis is the sieve curve, and you will see here what is retained by the membrane. So you will see here 3 very, very different filtration behaviors, while we have here a very sharp increase, meaning that we can distinguish between smaller pore size differences. We see here in the blue one a very slow increase, meaning that we are, we can cover a wider range, but are not efficiently filter or use the membrane as a filter for the different pore diameters. what is important here, or what is one of the characteristics normally for membranes, it's a pore size cutoff. Normally you look at 90% retention and then specify what pore diameter is retained with 90% retention. So let's have a look how it works. Experimental is quite easy or quite common. You prepare a so-called stock solution, and this stock solution is made of a broadly distributed reference materials. Use the simplest molecule or the simplest chemistry that is available. For example, in organic solvents, I would use polystyrene. In aqueous solvents, I would use a dextrane or a polylane, depending on the pores I would like to investigate. Then you filter this stock solution through your membrane, and you will have a filtrate at the end. Of course, not all the molecules should go through the membrane, because this is what we want to see. We want to see which molecules are kept back by the membrane. Once you have the filtrate and the stock solution, you just use those as samples in size exclusion chromatography. So you will inject them and you will get two chromatograms. You see here in red the stock solution overlaid with a filtrate here, and you see that all the higher molecular weights did not pass the membrane. They are there in the stock solution, but they are not in the filtrate, meaning that the membrane did not allow them to go through. Let us see what we can then do, because here we just have two chromatograms, nothing more. What can we do, or what do we do now? Well, we use a specific sieve curve formula. This depends again on what kind of membranes I want to investigate. I definitely always need the stock solution. Most of the time I always use the filtrate or different filtrates, and sometimes also people investigate the retentate, meaning which is left over. And these 2 or 3 curves are then combined into one sieve curve. How does that look like? You see it here. Let us have first a look at the left-hand side. The red trace again is our stock solution. And here you see 3 different sieve curves already. The dark blue one here shows us that either this is a truly bad membrane because you were not able, it was not able to retain to 100%. All the molecular weights are going through and nearly in all the same amount, or that you have made a mistake with your filtration experiment. So this one here definitely needs a check. But however, you already have a sieve curve. Unfortunately, it is still over elution volume, and this is not what you're looking for. You want, of course, molecular weights or pore sizes. So what do? Just what you always do in size exclusion chromatography. You do have a calibration curve, and then you can transfer your chromatograms into a molar mass distribution or into a sieve curve now plotted over the molar mass. And I said use a very simple molecule so that the chances are that there is a known relation between the molecular weight and the pore size, as it's shown here. If this is the case, if you do have these, if you can find these parameters in literature, or if you do have them already at your company, then you can not only have the molar mass here, but you can also plot your sieve curve against the pore diameter, and you can determine, for example, the pore size cutoff at 90% retention, or at any other retention volume you are looking for. So with sieve curve analysis, it's quite straightforward. You just measure your samples on a GPC SEC system, and then you just use the traces and calculate a sieve curve from that, and you can use calibration and conversion to pore size to get your complete sieve curve information. What else can we do to measure pore sizes or pore size distributions for porous materials? For this, I want to go back to the calibration curve we have already discussed. And nearly all GPC SEC experts that I know, when they look for a column, they do not look for the molar mass separation range, like from going from 100 to 1 million. They look for very detailed information, which is the calibration curve. The calibration curve reflects the pore size distribution and therefore describes your column material very detailed. Keeping that in mind and going back and defining sample in a different way, you can maybe already guess what inverse GPC SEC means. In inverse GPC SEC, we perform a completely different analysis. We use our sample as column material, which means we pack our sample into a glass column. Fortunately, the packing efficiency is not important here. And then we measure again molar mass standards to create a calibration curve. And then we can transfer this calibration curve using specific data analysis, like for example, our Pore track software. We can then transfer this calibration curve into the pore size and into the pore size distribution. For which samples does this? Can inverse GPC FEC applied? It can be applied for all solids with open pores, for all porous particles. However, it's not suitable for gels, for example. The advantage is that you characterize your particles in their native state with just general LC equipment, with just normally untoxic, non-toxic solvents. You don't have to use other techniques, and it's possible to cover a very wide pore size range from 0.5 to 600 nanometers. So how do the results look? You see what we did here. This is the cholesterol blood absorbing cartridge, which has been characterized. We used aqueous GPC SEC here with polyolane reference material, so basically non-toxic solvents non-toxic solvents. And our analysis here showed a bimodal distribution of very small active pores here and very large transport pores. And you see already the advantage again when you use a fractionating technique, because if you would not have used a fractionating technique, you would just have gotten an average of both of those pore sizes in one value, and you would not have seen the amount and the pore sizes, and that it's eventually a bimodal pore size distribution that you're looking at. In addition, you can also calculate the optimum size of a gas molecule, which is in this case 1.5 nanometers. Last but not least, there are 3 more slides I want to show you. We're really nearly out of time, but I think I'll make it with the 3 more slides. And I think it's very interesting because we are going now even bigger. We had the molecules, we had the porous materials, and now we look at some particles. And again, a typical GPC SEC chromatogram can show us why we can use a kind of GPC SEC, or at least a kind of size exclusion chromatography, to investigate particles. This is how we show how a separation on a typical GPC SEC column occurs. We have here in blue our particles, in white our pores, and in gray our interstitial volume. Interstitial volume means that before the exclusion limit, nothing can elute. Then we have the typical GPC SEC separation, which takes place in the white pores here. We have here a separation range of around from 4.5 to 12 milliliters, so around 6-7 milliliters, where we can eventually separate according to size. What if we do not separate in the pores, but in the interstitial volume? We can also have a separation there. And this, for example, can be used for particles. Examples or fields of applications were polymeric lattices, emulsions, dispersants. We can look at colloids, surfactants, or liposomes. and have again the advantage that we do have a fractionating technique. How would the experimental setup be? Very similar to a standard GPC SEC. However, this requires a few special treatments. For example, it requires special columns. We will not use GPC SEC columns because we are not interested into any pores. It also requires a specific eluent with special additives, but of course that's normally easy to do. Calibration, we use polystyrene particle standards instead of the molecular weight standards. Important is that we inject them together with a marker so that we can have a very reproducible elution. Detection would be UV because we use polystyrene particle standards here. And data analysis itself would then be a two-stage data analysis. First of all, we need a correction of band broadening, and then we need to get our distribution information. And for both of these, the calibration with the polystyrene particle standards is used. How does it look like, and what do I mean by that? Well, first of all, let us look how the calibration or an overlay of the different calibration standards with the markers would look like. You see here on the right-hand side the marker. It looks like one peak, but it's the marker for all of the peaks, so we get a very reproducible elution here. And then we see here our standards eluting in decreasing with decreasing radii. We start with 1000 going down to 46 nanometers here. However, what I want to show you, or what I want to emphasize here, is when you look at the axis, most probably you won't be able to read the numbers, but I can tell you that we go here from 12.5 milliliter to 14.5 milliliters. So we roughly have 2 milliliter elution volumes to cover all of these reference materials. When you compare it, to what we had when we do true size exclusion chromatography, like the 6.5 milliliter here, you will certainly agree that we have a very, very small separations range here. And this emphasizes again the need for a band broadening corrections. So how would a real sample look like before and after data treatment? On the top left, you see here a sample, a bimodal sample. Here on the right-hand side, again, the marker. We'll just ignore this and just look at the two peaks here. They are again shown here in black, and we see that definitely band broadening is an issue here, and that we can correct this band broadening with the results that we do have from our calibration curve, and we can get this blue curve here, which is our band broadened corrected data. If we recalculate again, if we iterate again, we'll see that we truly match the original data with that. So the red curve here is just our proof that the algorithm has worked properly. We don't see any difference or very, very small differences to the original data. So we can see here that the algorithm we used for correcting the band broadening has been applied successfully. And then we do nearly the same as in size exclusion chromatography, with the difference that we look here at different sizes of our particles. And you see here the bimodal distribution again, like we have one peak with a size of approximately 330 nanometer, and the other particle in there has approximately a value of 800 nanometer. So this is a very nice and elegant technique to look into particles, and also at least fits into the family of size exclusion chromatography. And with this, I want to show my last slide, which is a short summary of what we've covered in this presentation today. I could show that GPC SEC allows for non-destructive separation of complex mixtures, such as molecules always are, with respect to their size. GPC applications range from simple sample comparison to product deformulation, like as in a part of two-dimensional chromatography. We have multiple options for the determination of the molar mass distributions for homopolymers. And this molar mass information is extremely important that a product can be classified as a polymer. We can determine composition as well as determine branching. It is possible for selected examples. However, other methods should also be taken into account because it might be that not all of your questions can be answered with just using size exclusion chromatography. And then we had different applications from just molar mass or compositions. We have been looking to determine pore sizes and pore size distributions, and we have seen that sieve curves, or learned that sieve curve analysis or inverse size exclusion chromatography can be used to measure these parameters. And we have also looked at some particles where we had looked at separations in the interstitial volumes to determine particle sizes and more important, particle size distribution. And my very last slide, I want to thank you for your attention and let you know that we're happy to answer questions. But of course, I also need to mention my PSS colleagues who contributed with data to this presentation. Peter Montag is doing our high temperature GPC analysis, and he has provided all the data for the polyolefins. Friedhelm Gors for heparines, Wolfgang and Huub have provided me with the data for the HTC particle analysis, and Peter Kills has provided data for the pore size analysis and for the starches. And with that, I hope that we still have time to answer some questions, and that there are some questions I could, that Derek could let me know of.
Well, first of all, thank you, Danny, for this very interesting presentation. And we do have a few questions revolving around calibration curves, interestingly. So the question we have is, why is it so important to cover, or to make sure that you cover the whole range, this whole separation range of a column or column set with the calibration standard instead of just using a smaller range that covers the sample?
If your sample is fully covered, or if all parts of your sample are fully covered, then it is sufficient to use or to just cover that range. But however, it is really important that you just do not stop at the borders, like that you say, okay, the highest amount is 10,000 and I'll stop with 10,000. I think it's really important that the last calibration point has not that, is not 10,000 then, but like 20,000 or 30,000. Of course, you don't need to go to 1 million or whatever, but at least at the extremos, there should be some calibration standards so that you can really fit your data nicely. But of course, the most important part is that the range where your sample eludes is covered.
Thank you, Danny. And then another question that I have is, why, or basically, what's the advantage of using the molar mass distribution, so the W log M versus molar mass, instead of just using the detector signal versus the molar mass that basically ties into the same area?
So you mean like, why do we really need the molar mass distribution and not just the allogram?
Just the chromatogram, yes.
Mm-hmm. Because the chromatogram depends on the resolution of your column. For example, if your column loses resolution, it might be that your peak becomes narrower with time. If you do not monitor that, or if you don't have any idea that the resolution changes, you would think that there are two different samples. Yeah. And of course, you also cannot compare samples between different labs. For example, let us be an example, Derek. I'll get a sample from a customer and I'll measure it on my favorite equipment using three separation columns. And you get the same sample and you measure it on your equipment using your two favorite, let's say, linear M columns. Yeah, because you're looking more for time than I would do. So the chromatogram that you would get would be totally different. Your sample would elute at a different elution volume than mine, because you have two columns and I have three columns. In addition, if I have an older column set where the resolution is not as good as with your 2 linear columns, yeah, my peak would look smaller than your peak. So we could not compare the samples because a chromatogram is always combined information from the equipment you're using and from the sample itself. And only when you apply the calibration curve, only with this calibration curve, you, let's say, strip it back to just contribution from the sample. So this is sample and instrumentation information, and the molar mass distribution is plain sample information.
Yes, I think that makes sense, and I would hope that this answers this question. And then we have another question regarding the copolymer analysis you did at the beginning, when you were basically comparing RI and UV data. How do we account for the molar absorptivity of the sample in the UV? So basically the fear is that when you have different concentrations of the sample in there, wouldn't that also have an influence on what is observed in the UV trace?
At the moment, I'm still struggling a bit of which example we were looking at, because for copolymer, I've only showed the IR
Maybe it was not the
data.
copolymer, and so that's my bad. I thought this popped up during the copolymer slide.
Okay, yeah, yeah, mainly because I was mentioning the sorry that I'm scrolling through the slides. I'm sorry, because I was mentioning the 2D polymer here. Because in this case, for example, for a polystyrene PMMA graph copolymer, it will make sense to use a UV detector and a PMMA detector. A UV detector for the polystyrene and a RI detector for both the polystyrene and the PMMA, and do dual detection here. Yeah, that would make sense. But the question was, or what was the fear in that case?
The question is basically, how do we account for the difference in molar absorptivity at different concentrations? So in other words, the way I understand it is, there is a fear that when you're using the UV detector, the concentration dependence will give you different UV traces, basically. I think that's the way I understand this question.
Let me go back to this one here. What we see here is also, I think it's comparable here, because you see the different response to the different concentration in every slice. And actually, this is what we are doing. We are addressing every single slice here and the different concentration in here. Here in this case, it was a simple example because we just, divided the curves by each other. What you can do is, when you know your extinction coefficient, for example, with your UV detector, or when you know your detector response for an RI detector, you could have like 4 different responses. Yeah, you have a response for substance A with 1 detector, and for substance B with 1 detector gives 2, and the same for substance 1 with detector 1 and substance 2 with detector 2. So you have like 4 different response factors, and with these 2 different, you can solve the 2 different equations, and you can actually calculate the concentration in every elution volume slice with that. But for that, you need to have, for example, the extinction coefficient or your RI response factor. Does that help, or do you have a comment on that?
I think that was a very good explanation, and I will see. It's one of my customers, so I will take that upon me personally to follow up if that was a successful explanation. The customer just replied that was what I was looking for, so seems to be good. And then we have, if you want to stick around for another minute or two, another question I saw is, do we sell an infrared detector? Because you mentioned it, I think it's right on that slide that you have here.
Yes.
And the unfortunate answer is, for GPC, we don't.
No. This is only part of our high temperature equipment that we do have, and still the problem is that with ambient, the applicability of an IR detector would be very, very limited due to the solvents we need to use there. So answer is correct that you gave. It's unfortunately no, only for high temperature GPC.
And then could you maybe highlight again, and I think that ties in more to yesterday's demonstration of WinGPC in a way, but I think you mentioned universal calibration at one point, and the question is, could you elaborate on universal calibration a bit? How can you do it, and how can you use it during analysis?
Yeah, let me just go to this slide here, because I mentioned here that we have two ways for universal calibration. First of all, the universal calibration with a viscosity detector, where we measure actually the intrinsic viscosity of our standards and of our samples. And in this case, we plot a so-called universal calibration curve, meaning that I plot logarithm of intrinsic viscosity times molar mass versus the illusion volume. Basically, this is hydrodynamic volume versus illusion volume. So we calibrate absolutely in a way, and you can use this calibration curve for all kinds of chemistry. It doesn't matter if your sample and your calibrants have different chemistry, you can always use this universal calibration curve. It will apply to all different chemistries. On the other hand, there's a so-called mathematical approach to that, which means if I do have Mark-Howing coefficients for my calibrants and my sample, I can transfer calibration curves into each other. For example, I can calibrate using polystyrene. I know the Mark-Howing coefficients of that. I can analyze a polymethyl methacrylate. I also know the Mark-Howing coefficients of that. And what I'll do is I transform my polystyrene calibration curve with a mathematical algorithm into a PMMA calibration curve, so that I can measure true molecular weights, for example, for my polymethyl methacrylate samples. This is a very different approach from the viscosity detector approach, because with a viscosity detector, of course, I can measure intrinsic viscosity and Mark-Howing coefficients.
All right, and thank you for that explanation. And I think we can round it out with the last question that I have here, which is how much do the MW averages of a polymer change if you do not apply band broadening correction?
Oh, that's a very tough question. I'm sorry that I don't have an answer to that, but I at least know whom I can ask. As I mentioned, my colleagues Wolfgang and Huub, they've done quite a lot of work on that. If you don't mind, I would just ask Wolfgang and Huub if they have already investigated that. But all that I've shown, that I've seen so far, it really shows that this band broadening correction is truly important. I don't think it would work without that, honestly. But please let me try to find out if I can provide some real numbers, and I will talk to Wolfgang and Huub.
All right, and I think that concludes the questions that I have here. So again, Daniela, thank you for this interesting presentation, and thank you everybody for attending. I think there is also like a 3-question survey when you exit out of the webinar. We would welcome your feedback on that. And as I said before, there will be the recording of this webinar will be made available. And if you would like to have a copy of the slides, feel free to send either Daniela or myself an email. And with that, I would like to thank you again for attending. And as I said in the introduction, good morning, good day, or good evening, wherever in the world you joined us from. And have a great rest of your day.
The same from me. I would like to thank all of you for your attendance and hope to see you soon or hear you soon at the next PSS webinar. Goodbye.